First, let me introduce myself. I'm Andy Winnick. I'm the president of the American Institute for Progressive Democracy, which is a Claremont-based think tank, which is oriented towards both policy and promoting action. And we are the primary organizers of the conference today. There are 4 co-sponsors who have been working very closely with us. The Three Valleys Municipal Water District is one of our sponsors, and their executive director, who had hoped to speak today, will not be, but we have members of their board who are here. Scripps College is a sponsor and has donated the use of this auditorium and also the lunch facilities, which I'll talk about in a minute. And they are also providing a recording capacity, so the entire conference will be recorded. So you can tell your friends and colleagues that if they wish to see it, we hope to have it sometime between the middle and end of next month, March. I guess today's March 1st, so between March 15th and April 1st. It will be available on the Scripps College website, and also there'll be a link on the website for our institute, the taipd.org website, so you can catch up on stuff you may have missed. I want to welcome a lot of some of the dignitaries who are here today. They're representatives from the mayor and the city council of Claremont, mayor and city council member from Malibu, member of the Water Commission from Glendora, and I believe there are some others here as well, so I want to welcome them. The other co-sponsors of the conference is Pomona College and the Environmental Analysis Program, which is a 5 colleges program. That's a program that spans all 5 of the Claremont colleges. And finally, the Robert Redford Conservancy for Southern California, which is housed at Pitzer College, and they are the other co-sponsor. So it has been a joint effort, and there have been faculty from some of the other colleges who are also working with us. So this is a broad effort. Let me make a couple quick comments about the theme and the planning for the day. Our concern when we decided to put this conference on was that there are lots of conferences that focus on small aspects of the water problem. But we felt that what was really important was to do something that was really comprehensive and pointed to the interconnectedness. And so as the title of the conference suggests, we want to start with the global perspective and climate change and get a feeling for how that obviously has major impacts. We will then talk about the national policy, and there are key issues in this country, obviously, and every country that involves national water policy, and obviously water is not a respecter of state boundaries, so the issues clearly cross over on a national basis. Then in the afternoon session, we will start with a discussion about California as a state, the water policy. Obviously, as most of you probably know, there are major issues involving the transport and moving of water from the north to the south and what have you. And so there really is a state issue with regard to water. And then finally, the afternoon session is an attempt to focus more on solutions than on problems, although we're hoping that all of the speakers will address both. And we'll look to the issue of 5 speakers who will talk about various aspects of water solutions to the water scarcity problems over the future in Southern California. So that's our schedule. Lunch is available, and I'll talk more about that at the end of the second session, but there is a very nice dining hall that's available to us, which is a 5-minute walk from the auditorium, and you're all invited to have lunch there. Normally off-campus guests pay $12.50, but if you pick up a little red ticket on your way out the door, you'll get a reduced price of $7.25. So if you want to have lunch, you're very much invited, but get your little red ticket and tell them you're part of the conference. Finally, let me see. I think that's about it. Okay, so what I want to do is get started right away. The format will be that we'll have the speakers presenting for the first 50 minutes to an hour of each session, and then we'll leave the last 20 to 30 minutes at the end of each session for questions and answers. There'll be 2 microphones, as you can see here, and we'll have people. You do not have to come up to stand in line. We'll have people from our board who will go around to you, so just raise your hand, and they'll come to you with your questions or comments. So without further ado, let me introduce the speakers for this morning's session. We have 3 faculty members. Heather Williams will lead off. She's a associate professor of politics at Pomona College with a specialty in water policy. She's also done a great deal of work in Latin America and elsewhere on water policy, as well as in Southern California. Our second speaker is Richard Hazlett, who's a professor of geology and the Stephen Pauley Chair in environmental analysis at Pomona College. Again, he will be getting a sense from sort of the scientific side of the water issues on a global basis. Branwen Williams is an assistant professor of environmental science. She's with the Keck Science Department, which is a 3-college program with Claremont McKenna, Pitzer, and Scripps College. And we owe Branwen a special vote of thanks. She was at a conference in Hawaii and flew in and arrived at LAX at 6 o'clock this morning. So that was a major effort. So, all right, so without further ado, Heather, we'll start with you.
Thank you so much, Andy. The headlines are heart-stopping. Here in the U.S. West, drought is felling forests and draining reservoirs and threatening to leave our cities high, dry, and without enough power. In the Near East and Central Asia, drier weather is draining aquifers that supply major cities. In Northeast Africa, the race for the Nile River Basin is heightening tensions among already fragile governments in Egypt, Sudan, South Sudan, Ethiopia, and Eritrea. Meanwhile, in the Middle East, a dam complex in eastern Turkey on the Tigris and Euphrates rivers flowing south into Syria and Iraq may cause great shortages in regions already plundered and impoverished by war. In China, India, and Brazil, the world's emerging great powers, they're making plans for massive rerouting and engineering of their river basins to accommodate growth and bring water to arid lands. China, for example, is lifting portions of the mighty Yangtze out of its banks in the south of the country to its parched industrial north, where the Yellow River has become too degraded for use. In India, meanwhile, there's now serious consideration of a $140 billion project to interconnect its great rivers to meet rising demands for power and water and to compensate for aquifers that are being rapidly depleted. In Australia, the world's least water-endowed continent, they're now experiencing hyperheated summers and prolonged drought, with interior temperatures averaging 120 degrees in the hot season. The list goes on. And frustratingly, at this very juncture, when climate change and continued population growth would seem to indicate the necessity of extraordinary measures to conserve water, many projects are being undertaken, are being done to increase countries' per capita water use in the name of more growth, more land under cultivation, and more exports. And at the same time, water as a basic need is not being met for great numbers of people. It's estimated that somewhere between 780 and 1 billion people in the world currently lack access to safe, clean water. According to the World Health Organization, deaths from polluted water outnumber deaths from any of the major epidemics, including tuberculosis, HIV/AIDS, and malaria. So it leads us to this awful question: is there enough water for all? Do we really have hope of seeing to it that there's enough water on an increasingly crowded planet with hotter summers and drier, arid regions and wetter and saltier flood-prone areas, particularly on the world's coasts? My answer, believe it or not, is yes. I actually believe that our failure to meet the challenge of providing tomorrow's populations with safe access to adequate, safe water would not only be a shame, it would be a scandal. In the following short talk, I hope to convince you that we do have enough fresh water in the world for all to thrive. And if the global community is determined to defend freshwater supplies for the coming generations, and we are mindful of the importance of defending diverse uses of water, shared freshwater supplies, instead of being a detonator of conflict, could be a bridge to peace and greater cooperation inside countries and also between them. I say this not as a pipe dream, not as a feel-good early morning speech designed to make people feel like it's worth it to stay and grapple with a complex and somewhat scary topic. I'm actually serious. As an aside, One of the reasons I study water is because I never doubt that it's important. I never wake up in the morning and say, gosh, who cares about water? The second reason I study water is because as a political scientist, I am very interested in the way that people spar over a scarce resource. You can look at the Nile or the Brahmaputra or the Danube or even our own Santa Ana River to get a sense of the knockdown, drag-out fights that will rage between upstream and downstream water users. As the historian Karl Wittfogel once argued about arid lands kingdoms in the ancient world, what he called hydraulic civilizations, control of water supplies in dry regions is critical to the business of ruling. The more effectively people's labors and their taxes are tied up in the control and the conveyance of water, the more power accrues to rulers at the top. But you know, the third reason I study water is because while the conflicts are actually colorful and they're intriguing or they're terrifying in some cases, the solutions that people reach over water are even more interesting. And they account for some of the greatest advances in the quality of life in human history. Many of the technologies and the forms of participation that have emerged around water, both in traditional rural societies as well as urban and more statutorily democratic societies, show the possibilities for bringing diverse groups of people together with experts to build arrangements for resolving disputes and allocating clean water peacefully and equitably. Now you may be thinking, like, what is this person talking about? Well, consider something that we barely even think about here in California. Water treatment is one such solution that addresses an inherent conflict between those who discharge wastes into waterways and those who need that water for use in their homes or on their farms or who fish or swim in that water. Water treatment for domestic use, for example, has extended lives in the last 100 years by more life years, probably than all the medical procedures combined that have been performed. And it's incredibly cheap. You know, a heart bypass surgery these days is what, $50,000, $100,000. But each year of life extended by clean water delivery, by contrast, per person is in the pennies. It's one of the best, most cost-effective things that can be done to improve life for all. Likewise, end-of-the-pipe treatment and pollution regulation, though more expensive, controversial, especially among polluters, and energy-intensive, is also a great investment in peace, health, prosperity, and quality of life. So what I want to argue is this: there is enough water for all to thrive. However, I won't kid you, water is scarce. And what do I mean by scarce? I mean it's scarce because there isn't enough water, not even close, for all to get everything they want for all the purposes they'd like. The problem is, right now, is that those who'd like water for greater luxuries and wealth enhancement, such as additional hydropower or water for vast soybean or biofuel plantations or for gigantic gold mines or for golf courses in the desert, at this point are often in an excellent position to secure public money and government endorsement for large-scale river basin engineering and big takeouts of groundwater. I also want to argue that water scarcity as a global phenomenon is also a strange puzzle, though, because water, though it's globally important, is also an intensely local resource. While it can be transported over considerable distances in aqueducts, it nonetheless is something that exists in time and place. And so the solutions that are available in some basins won't be applicable to others. There is no one-size-fits-all for solving water conflicts, and so the principles that need to be applied for finding solutions have to be sufficiently flexible to accommodate local geography, politics, cultural understandings about the meaning and purpose of water and waterways, and development needs. For example, in the Okavango Delta in southern Africa, it's a question of balancing needs between the urban customers in Namibia, who actually use very little water per capita, but also protecting the gathering rights and fishing grounds of people who live downstream in marshes and swamps. In the lower Mekong, it's about protecting the rights of Cambodian and Vietnamese fishers versus upstream hydroelectric plants. In the highlands of Peru, where I do a great deal of work, it's also about compensating for dropping springs, for drying up springs and dropping well levels because of receding glaciers and also contamination from mines, which have become the engine of that economy. In Mexico City, it's about depleted aquifers and an aging, overtaxed distribution system. So these very diverse problems are one reason why I haven't developed a lot of graphs showing you a global availability of water with some neat graphs with per capita allocations and some nice plans for the future. The truth is, with water, as wet as the interior of the Amazon is, or the middle of Kauai is, and as dry as Namibia is, they're not getting connected anytime soon. And as might happen with, say, something like medicines or foodstuffs. Water, more than any other scarce resource that sustains life and livelihood, is anchored to the physical planet. As much as the 21st century seems to suggest that everything we are and everything we need can be made abstract, can be done online, can be traded over borders, can be bought with bitcoins or PayPal accounts, water actually brings us back to where we are, physically, on the planet. Ultimately, it's too heavy, too unwieldy, and needed in too great a volume to be trucked around like wheat or corn or aspirins or iron ore for all the purposes it's needed for. Those plastic bottles from Fiji or whatever, you know, actually they're a big problem for certain local supplies and can be a problem for landfills, but ultimately, it's a very small amount of the water we use. The truth is, no matter how clever we get about recycling water, storing it, wheeling it in pipes across the land, we, like our ancestors before us, are utterly dependent on the skies and on the water cycle to renew the water in our basins. So ultimately, if we are to have enough for all, what is needed for us is to roll back the language of globalism, where we imagine instantaneous transfers of information and money, of mutability, of identity, and remember that some things, like rivers, may flow as slowly as a man can walk. And water percolates through the ground even more slowly, sometimes inches, even millimeters per year. So ultimately, if you don't know the basin you're in, you might not know where your water is coming from, but your activities, your presence in that basin leaves a mark on it and has an impact. So insofar as our water arrangements remind us where we are on the physical planet, I think that we may come closer to providing water for all. So reviewing the Dublin Principles that were fashioned about 20 years ago to provide a framework for countries to address water resources, they assert the following. The first principle is that fresh water is a finite and vulnerable resource, essential to sustain life, development, and the environment. The second principle is about participation, saying water development and management should be based on a participatory approach involving users, planners, and policymakers at all levels. The third is about gender. Women play a central part in the provision, management, and safeguarding of water. And the fourth principle, a very controversial one, given many people's feelings about water as a human right versus water as a scarce good, says that water has an economic value in all its competing uses and should be recognized as an economic good. To these, I wish we could add a fifth principle that would be a shadow principle, saying that water comes to us through basins in the physical earth, and the care and protection of that water must be the responsibility of those who live in it. So ultimately, if these principles are to work for us and the many non-humans with whom we share the planet and who also need water for life, the principles have to be recognized at a basin level, where the following kinds of land use and land-based problems must be reviewed democratically and openly with a mind to what balance can be achieved between the needs for present livelihood and the long-term need for sustainability. The first thing I would beg for people to pay attention to in their work as water activists or simply as engaged citizens, the first is extractive activities, including drilling, mining, and underground injection of waste. One of the greatest losses we could possibly sustain at this time is the loss of the world's natural storage of fresh water. Here we face a choice. Do we want to get everything we can out of the earth, or do we also want to be able to put precious water back in the earth, or let the earth's natural systems absorb water and store it for us? We see that dilemma out here in California with hydrofracking and other kinds of injection of waste into the ground. We see it in oil drilling in the Amazon or Canada's tar sands. We see it with gold and metal mines in South Africa, Bolivia, Ghana, Afghanistan, Papua New Guinea, and a host of other countries. So if we are to provide enough for all, the use and conservation not only of land but also of subsoil must be the subject of local review and local monitoring, local regulation, and yes, even local injunction. A second issue that I think is absolutely critical for water for all is attention to large dam building, especially in the Himalayan watershed, where half the world's population gets its water. Much as we saw in the 1950s and the 1960s, the 2000s have again become an era where rising powers are racing to the rivers. Rapid-fire dam building has enormous consequences for the world's remaining wild rivers, which are not only a critical source of water for people, but they also provide much of the available protein in fish to the world's poor. It must be decided, will ideas about impact assessment and public participation be brought to bear in the design and financing of massive river structures? And if not, who pays for that damage? So here I would call for renewed commitment to the groundbreaking work of the World Commission on Dams, which in 2000 established guidelines for project design, local review of projects, and elimination of projects that are likely to cause a great deal of damage. The third thing I think is an absolutely critical thing is attention to sea level rise and saline intrusion into aquifers, marshes, and deltas. Climate change is having an enormous and observable impact in patterns of precipitation, but an even greater impact on freshwater supplies may come from ocean pressure on freshwater basins. So much as with extractive activities, we must consider what the loss of natural storage means for our ability to supply populations with water. And finally, I think we need to pay more attention to management of discharges into waterways and enhancement of treatment and recycling facilities, both at a large and a small scale. As said earlier, even though in the moment this may seem like a huge investment, especially given the opposition of many industries to taxation or regulation and the resistance of many governments to dealing with the very non-sexy issue of waste, this is perhaps the most cost-effective way of extending lives, avoiding illness, protecting the most vulnerable, and extending the number of uses that water can serve. So time is short, and I fear that my time is already up. I hope that these slivers of ideas may serve to open a fruitful conversation today. I'm really excited to hear the presentations from others, and I wanted to thank you for the opportunity to speak at this conference, and my thanks also to Andy for doing ever so much to make this happen. I look forward to hearing from all of you today. Thank you.
Thank you, Heather.
Pardon me if my voice sounds a bit gravelly. I'm coming off a head cold. It's part of the collateral damage of teaching in a petri dish. But anyway, I think I'm almost there. Good morning, and thanks to the American Institute for Progressive Democracy for inviting me to contribute. This morning I'll amplify some points that Heather's just presented, focusing on the third dimension of our water picture, what lies unseen as stored water in the earth. Let's begin by considering this figure from the Water Replenishment District of Southern California. It shows how the annual precipitation has varied historically at the Los Angeles Civic Center over the past 130 years, up until 2007. The blue bars are the actual annual totals of rainfall measured. Note the tremendous variability. If one were to base water use entirely upon rainfall storage in cisterns, then a conservative approach would be to restrict water users in Southern California to an expectation of less than 5 inches of rainfall per year, which technically would define our landscape as a true desert. In other words, millions of people would have to leave our landscape. But the historic average annual rainfall, shown by the black horizontal bar, is in fact about 15 inches, a bit more than what would climatologically be defined as desert conditions. So it's more appropriate, really, to refer to the plains of coastal Southern California as, an oak, sage, savanna rather than a desert under natural pre-settlement conditions. This figure illustrates that owing to variability, precipitation alone is an insufficient basis as a primary water supply in many, if not most, parts of the world. See if I can get this gizmochi to work. So we can import this water, and we can gather that water in reservoirs mainly to stabilize and collect supply. Another answer, which I think is more important to us in terms of numbers and economy, is to find stable reservoirs of fresh water underground in what we call groundwater. If a rain is slow and steady, much of this water will seep into the earth, typically infiltrating at a speed no greater than that of a garden snail moving across a patio. That water keeps seeking until the cracks and pore spaces in the ground close up owing to great pressure deep below. Then it backfills those cracks and pore spaces, creating an underground body of water or aquifer, the top of which is a horizon we call the water table. The volume of water in an aquifer is controlled on the one hand by its slow outflow to lower elevations, and on the other by imports of freshly infiltrating water. Water may be stored in an aquifer for thousands of years. An aquifer is sort of a natural savings account of past infiltration that is freshly replenished in minor seasonal increments. The average recycling time for groundwater in North America's aquifers is roughly 1,400 years. In contrast, all of the water in even the largest surface river will be replaced with fresh supply in less than 20 days at most. So when we pump out groundwater, we're usually pumping out stored supply that takes many human generations to replace. Therefore, we need to think of our water supply situation as a three-dimensional matter. The problem with this is that the state of something which is generally out of sight, as groundwater surely is also out of mind in terms of public perceptions, even of policy and basic accountability practices. Unlike air pollution, for instance, groundwater pollution is something people can easily dismiss, provided that the water coming out of one's tap is clean and tastes fresh. Fresh, clean groundwater is more important for human civilization than fossil fuels by far. It is the ultimate limiting resource in terms of agriculture and human population. It's the primary drinking water supply for 1.5 billion people who could not live without it, including 95% of the rural U.S. population. And demand is rising, now from industry as well. On average, a ton of water used in industry generates roughly $20,000 worth of output, which is about 70 times as much profit as the same amount of water used to grow grain. At present, about 20% of total aquifer supply worldwide is diverted to factories, putting an increasing squeeze on other water uses, as Heather emphasized in her talk. The problem with groundwater is poor global stewardship, complicated by transnational, interstate, and corporate interests. And it can be broken into three overarching categories. Overdepletion, incentivized by an economic system that's designed, well, substantially to overdeplete. Groundwater pollution from poor waste storage and management, and deliberate groundwater pollution to remove the worst liquid wastes from expensive surface storage options. Let's consider breezily these three categories in turn. As implied by the stats I've already provided, we are over-depleting our principal groundwater stocks through well construction and pumping at a rapid and growing rate. Just how serious is this depletion worldwide? We don't and can't know for sure. But available data show that this is at least a big and growing problem. An August 2012 study in Nature by the International Groundwater Resources Assessment Center examined over 700 aquifers of global significance. A map of their data shows degrees of aquifer exploitation stress, with warmer colors indicating areas of seriously substantial overdraft. The areas of most serious concern include the Middle East, northwestern Mexico, and northern India, which is the most threatened region in the world in terms of large numbers of people facing long-term water scarcity. Included in the aquifers of critical concern is the Ogallala, found in the American Midwest, from which almost a third of all U.S. irrigation water comes. At current rates of depletion, University of Kansas hydrologists estimate that this reservoir will be effectively gone in about 50 years. But depletion alone does not account for shrinkage in useful groundwater supplies. Pollution is another issue, as you've heard. The problem from wastes leaking unintentionally into the ground is enormous, and it isn't all people who are to blame. In the United States, farm animals produce 130 times as much waste as humans do, with millions of tons of pig and cattle feces washing into streams and rivers every year. Much of the nitrogen this material carries ends up in groundwater together with nitrates from fertilizers and various pesticides and herbicides. Consumed in high concentrations of above 10 milligrams per liter of water, nitrate contamination, as many of you know, can cause methemoglobinemia, a condition that can kill babies. At levels above 100 milligrams per liter, according to the Environmental Protection Agency, then this condition is highly likely to appear. In the U.S., the Geological Survey reports that 15% of our groundwater supplies exceed safe standards for nitrates. And in China, monitors report drinking well water nitrate concentrations of as high as 300 milligrams per liter. Wow. Even more impacted, or impactful, are carcinogenic petroleum products in groundwater seeping in from old, rusting, leaky gas tanks beneath service stations and motor pools. In Texas alone, over 90% of counties report leaky gas tanks, which the EPA has asserted have the potential to affect virtually every major and minor aquifer in that state. Then there's the deliberate addition of pollutants to groundwater. In the United States, this has been done both as a matter of potential need for national security and as an ordinary waste disposal policy. The Hanford site in Washington State, where plutonium was manufactured to make atomic bombs during the Cold War, lies astride the Columbia River. As a byproduct of plutonium production, engineers intentionally dumped 450 billion gallons of radioactive liquid wastes into the ground, creating 8 plumes of radioactive groundwater that are working their way to the riverbank much faster than anticipated. In fact, the engineers thought that it might take as long as 10,000 years for any contaminants to reach the local water table, an example of greatly oversimplified groundwater modeling. Without action, the Columbia will surely become radioactive as it flows past Portland, Oregon. But when? The Oregon Department of Energy states, quote, "We don't know when this will occur or how much waste will leak in, or in what concentrations," end quote. To deal with the problem, the government is spending over $150 billion on the largest environmental cleanup operation in the world. And it's not progressing very well, I must say. Well behind schedule in terms of planning. Even more generally surprising for ordinary citizens, I think, is the deliberate policy of injecting vast amounts of chemical wastes from industry and some municipal wastes in the form of raw sewage deep into American groundwaters. The idea is to place it underground where aquifers are stagnant and capped by impermeable rock layers called aquicludes. This quarantines the pollution more or less geologically. And if this isn't possible, then the waste can be legally injected into aquifers that are not being used, presently anyhow, for drinking purposes. Over 680,000 wells have been drilled in the United States to legally dispose of hazardous wastes. 9 billion gallons of toxic fluids go down the hole each year in this country. The underground sacrifice zones underlie broad swaths of America, especially in the Midwest. Why not just store it in secure landfills at the surface? Because landfilling would be too expensive for industry and city governments, and because too few landfills exist to accommodate the waste, with intense political pressure exerted to keep it that way. Not in my backyard, please. Added to this injection stream, too, are the toxic wastes used in hydrofracking. Hydrofracking. I hate that word. It's important, but the source of new American oil and gas boom. And these fluids are largely re-injected into the crust after the gas is extracted. These contain God knows what in terms of constituents. The ingredients are largely proprietary secrets, though they impact a public resource. And this is owing to business pressure on Congress and state governments. But we do know that these fluids include such substances as formaldehyde in the ingredients that go into shampoo, and that they have a serious impact on ecosystems if spilled at the surface. We also know that this stuff, irrespective of intention, is filtering into well-used public aquifers, as revealed in a few very critical recent studies. The reason is that we have no way of completely understanding the structure that governs groundwater flow except on a theoretical basis. U.S. Geological Survey hydrologist J.D. Bredehoft stated tellingly that no groundwater model we have ever created is unflawed, quite often in critical ways. Why do we do this? Of course, it's a powerful combination of economic expedience coupled with profound technical ignorance and short-term convenience. What must we do? There are many approaches you'll hear about today, but I'll wrap up my statement by quoting Payal Sampath, a World Watch Institute researcher. He says, quote, "In many places, various authorities and industries have fought back the contamination leak by leak or chemical by chemical, only to find that the individual fixes don't add up. As we lined landfills to reduce leakage, for instance, tons of pesticide may be running off nearby farms into aquifers. As we mend holes in underground gas tanks, acid from mines may be seeping into groundwater unchecked. Clearly, it's essential to control the damage we've already inflicted and to protect communities and ecosystems from the poison fallout. But given what we already know, that damage to aquifers is mostly irreversible and can take years before groundwater pollution reveals itself. The chemicals can react synergistically, often in unanticipated ways, and it's now clear that a patchwork response isn't going to be effective. Given how much damage this pollution inflicts on public health, the environment, and the economy, once it gets into the water, it's critical that the emphasis be shifted from filtering out toxins to not using them in the first place. Andrew Skinner, who heads the International Association of Hydrogeologists, puts it this way: prevention is the only credible strategy. Thank you.
Branwen Williams.
I thought I would start off showing a satellite image of soil moisture from last month, just to stress the importance of this topic despite the rain we've been having for the last couple of days. And I was invited today to talk to you about how our changing climate is going to influence our precipitation. And this figure in the bottom is similar to the one that Rick just showed, showing how variable our precipitation is from year to year. And that's a really important part of considering what our weather is. And my job here is to tell you how our climate is going to impact that weather. So to do this, I've divided this talk into 4 parts. First, I want to address what drives precipitation in California. Second, I want to talk about how and why our climate is changing. Third, how is a changing climate then going to impact this weather from day to day? And finally, we're actually going to delve briefly into the past drought of California and the broader Southwest to see what has happened naturally in the past without a human influence. So when you first look at this map of the variability, and you can see down here, that's our current low levels, although this number might change after this weekend. This is again in Pasadena, is this very, very high interannual variability. And so let's look at what causes precipitation in California. And first, to do this, we need to look into the tropical Pacific Ocean in the eastern tropical Pacific. This is a map of seawater temperatures, where the reds are the warmer colors, the blues are the cooler colors. The equator is right across here, and you can see the warm colors in the middle of the tropical Pacific. This is because most of the sun's energy, it's more concentrated when it hits at the equator, and so it warms this water. As the warm water interacts with the air, it's going to warm the air and cause that warm air to rise. As the air rises, it's going to cool, it's going to cause precipitation, and so you have high bands of precipitation where you have the warm water. And this is called a low pressure system right around the equator, and you see it marked by the clouds where you have the high precipitation. As this air reaches the top of our part of the atmosphere, the troposphere, it's going to diverge north and south of the equator, working towards the poles. As it works towards the poles, it's going to cool, and it's going to start getting more dense, and it's going to sink, coming down at about 30 degrees north and 30 degrees south, forming a high-pressure system. This high-pressure system is generally cold air that's very, very dry. And if you know the latitude of Southern California, about 34 degrees, we're in one of these high-pressure systems. And this, combined with our topography, and then also the cooler waters off of our coast, explains why we have a Mediterranean climate. Seasonally, now this map of seawater temperatures is an annual average. What happens is the band of warm temperatures moves north during our summer and then south during our winter. And that changes the atmospheric patterns of how the wind is moving. If we look at the summer first, so this is when the band of warm water is going to move further north. It's going to bring that band of precipitation with it, and it's going to change the atmospheric pressure patterns, so that there's going to be a high-pressure system in the northeast Pacific Ocean and a low-pressure system over the southeast or southwest US, right in here. And the way that the winds are blowing is going to bring down dry air over Southern California, and that's why we have dry summers. When we do get precipitation, it's because this low-pressure system here, the monsoon, actually moves a little bit to the west, but that doesn't happen very frequently. In contrast, in our winter, there's a change in the atmospheric pressure between the high and the low pressure, where the low pressure moves over into the Aleutians archipelago, the high pressure is offshore here, and then the way that the atmospheric patterns flow, and this is due to the seawater temperature, and it's also due to the fact that our Earth is spinning, it brings in moist air from off the ocean onto our coast. And if you think about when we get most of our precipitation, it's during winter storms that come on shore and they dump water as they move eastwards into the mountain range and over the continent. And so it's these winter storms resulting from this atmospheric pattern that brings us our winter rains. And that explains our seasonal variability. If we look onto interannual timescales going from year to year, this is actually mostly explained by a phenomenon called El Niño Southern Oscillation, which can be abbreviated to ENSO. El Niño Southern Oscillation is an interaction between the oceans and the atmosphere. And if we look at kind of normal conditions, it's not really normal, but if we look on a typical kind of average time of what it looks like, and this is the same map as what I showed earlier without the contours, we have warm water that's pushed over in the Pacific Ocean to the west. So we have trade winds that are blowing across the surface of the ocean, and they're pushing that water to the west, kind of like in a bathtub if you're going to pile it all over. What happens every 3 to 7 years is those winds slow down, you stop pushing that water over, and it actually sloshes back over to the east, bringing this warm water back over towards our side of the Pacific Basin. If you remember, the warm water heats the air above it. That air rises, it causes precipitation. As this warm water sloshes back, it brings precipitation with it. So during El Niño years, we tend to have more rain. And if you remember back to the map I showed you of Pasadena's precipitation, some of the high points in there were El Niño years. The highest one was 1982, which was a very, very big El Niño event. And we can look at it in a little bit more detail in terms of the atmospheric pressure systems. When you have, it's again, an El Niño event, your low pressure system moves east with all that warm water as it comes sloshing back across the basin, and with it, it brings an extended Pacific jet stream and amplified storm track, bringing wet weather across into Southern California. Now, the opposite of El Niño is called La Nina. And this is when the winds amplify, pushing that warm water even further over into the West Pacific. So over in here, you have even more warm water. There's amplified precipitation over in the Western Pacific, and there's often droughts. It changes our atmospheric patterns in the Eastern Pacific to form a high-pressure system that pulls the jet stream north and brings moisture into the northwest US, leaving Southern California dry. So during La Nina years, we tend to be very, very dry. And so the question we want to ask today is how our changing climate is going to impact both those winter storms and the El Nino Southern Oscillation to get an idea of how our long-term climate might change, which then impacts our day-to-day weather and precipitation. So just to do a little bit tangent to talk about how our climate is changing, I want to do a brief little kind of introduction to greenhouse gases. The sun's energy, most of the energy in our planet comes from the sun. It comes into our atmosphere as shortwave radiation. It's radiation with a wavelength that we can see. That's why sunlight looks yellow. Some of it is reflected in the atmosphere and goes back up to space. Some of it's reflected on the Earth, goes back up to space. But some of it is absorbed and warms our surface. Some of this absorbed shortwave radiation is re-emitted back up into the atmosphere at a different wavelength. It's now long wave radiation that we can't see, infrared radiation. And some of that goes up into the atmosphere, but some of it interacts with greenhouse gases and stays in our system, warming our system. Greenhouse gases like CO2 have specific properties that interact with this long wave radiation. And as we're increasing the CO2 in the atmosphere, what happens is more of this energy is going to be trapped and stay in our system, less of it is going to leave, and that's going to cause our system, our Earth system, to warm. Now, we've been increasing our greenhouse gases in the atmosphere. Carbon dioxide passed a milestone of about 400 parts per million recently, for the first time in our history. And we know this because of instrumental records. For the past 45, 50 years, we've been measuring CO2 in the atmosphere. You can see the red line here showing the seasonal variability. This reflects variations in atmospheric CO2 because of all the plants that photosynthesize in the summer and then respire in the winter. And the black line shows your kind of average trend year over year. And you can see it's gone up from 320 to about 400 parts per million. And we can put this into a longer term perspective and look at it over the past 800,000 years. We can do this because carbon dioxide is trapped into little air pockets in ice when ice is formed. And then it gets layered up over time in ice sheets and glaciers. And scientists can go and they can measure the carbon dioxide concentration in these ice records to reconstruct what atmospheric concentrations have been historically. They've been able to go back in Antarctica to 800,000 years, and you can see how it varies when our planet is warmer and colder over these periods in time. And to put in context, current values are right up here. And this is what they were before we started burning fossil fuels. And we know that carbon dioxide also oscillates with temperature. From the same ice cores, we can also extract what temperature was during the same periods in time, and you can see how temperature and carbon dioxide fluctuate together. So we know as we're putting more carbon dioxide into the atmosphere, we're going to increase the temperature. And we have evidence of that. This is a surface map showing the change in temperature over the past 100 years. Redder colors are warmer temperatures. The purples are about 2 degrees Celsius change over the past 100 years. The blue colors are cooler colors. And in some locations in the North Atlantic Ocean, because of oceanographic changes, it's gotten cooler. But on our global average, temperatures have increased by about 1 degree Celsius over the past 100 years, primarily because of this increase in carbon dioxide emissions. We can use computer models to project how temperature is going to continue to increase in the future. There's many different models out there, and they all kind of tell you something a little bit different. But if we look at the average projection from these models, using a scenario of kind of business as usual CO2 emissions, so it's not an extreme or a very conservative estimate, somewhere in the middle, we can see that temperature is going to continue to increase by maybe another degree in a half century to another century. So the question we have is, how are these projections of future temperature going to impact El Nino, and how are they going to impact our winter storms? If we first look at El Nino, and I'm going to go ahead and just give you the punchline on this, reading along the bottom, and this is from a recent intergovernmental report on climate change that we actually have low confidence for any projections of how El Nino is going to change. This is a figure showing model output, so what the models are telling us about future changes El Nino, where if we say there's going to be kind of more El Nino conditions or more La Nina conditions, the models tend to say more El Nino, but if it's increased variability or decreased variability, they really don't know. The scatter's all over the place. So what this is showing is we don't know what's going to happen. We think there might be more El Nino events, which would bring more precipitation to Southern California, but as a community, climate scientists aren't really sure what's going to happen. But if we go to what's happening with our winter storms, we actually have a better idea. So first, let's look at global precipitation. Just a reminder that we have our low pressure system at the equator where there's a lot of precipitation. Because of the atmospheric patterns, we have dry air at about 30 degrees north and south. And what's going to happen as we increase the temperatures, this tropical area is going to expand, and it's actually going to push this high pressure system further north. And so these are two model outputs, one of them looking at low carbon dioxide emissions, one looking at high carbon dioxide emissions. And what's pretty consistent is there's going to be the wetter areas are going to get wetter and the dry areas are going to get drier. So if you're already someplace with a lot of rain, you're going to get more rain. If you're someplace that's already dry, like us, you're going to get drier. And you can see the blues here are more rain, and if the high emission scenario, up to 50% more rain, but the drier areas are going to get drier. We can also use regional models that focus more in on what's happening in Southern California. And here the situation's a bit more dire when we look at what's projected. And what they think is going to happen is that that winter storm track is going to move north. It's going to be pushed north, and as it does, we're going to get fewer of those winter storms. And they project that under the lower emission scenario, we could have maybe 10 to 20% less precipitation on average, but under the higher emission scenario, it's 40 to 50% less precipitation on average. And this is at the end of the century, so in 2080 to 2099 relative to a couple of decades ago. So that's a pretty dramatic change. And there's already evidence that this storm track has been moving. It's moved northward. It's migrated northward by about a half a degree latitude over the past decade, or sorry, over the past couple of decades. So there's already evidence that this is occurring, and what we see with the model projections is it's most likely to happen. And so we could say that we're most likely going to have drier conditions in Southern California going forward. And one thing we can do to put that into context is look into the past to see what past variability in this region was like. And one way we can do that is looking at tree rings. This is a Douglas fir. And in trees that are growing in conditions where there's some environmental variable that's limiting, for example, precipitation, precipitation will drive growth. So that the tree is going to grow faster when there's more rain, and it's going to grow slower when it's less rain. And with many trees, when you cut them at the trunk and you looked at them, they have these beautiful growth bands, where each growth band is formed over a course of a year. So you can assign time to each growth band in the tree. And you can also measure the relative widths of the tree rings, so that in a wetter year, it's going to be a wider band, and in a drier year, it's going to be a narrower band. And if you have an instrumental precipitation record from nearby that tree, you can take those relative ring widths, which you can kind of measure and put into time, and you can convert that to absolute records of precipitation. And this is one way we know a lot about how climate, weather, and precipitation and temperature has changed in the Northern Hemisphere going back the past 2,000 years. Just looking at one such record that we have available, this is for the broader region of the Southwest US. And if you can look at the bottom panel first, this is going back a century, and instead of looking at a record of precipitation, it's looking at percent drought area. So how widespread is drought? And this record came out in 2004, so the last available data was the 2004 drought period. But you can see that while it was a dramatic event, in the recent past, there's been other events that were similarly dramatic. Now, if you move your eyes up to the top panel, this is the past 100 years, and we can now go back to the past 1,200 years. And what you can see is that on average, our conditions in the Southwest US over the past 100 years have actually been on the wetter side. And then if we go back into the past record, 1,000 years ago, conditions were on average much, much drier than they were today. And they're kind of highlighted by what they call mega droughts, decade-long periods of much, much drier conditions than what we have today. So what this is saying is that we've actually been living in a period of time that's quite conducive to living here, that if we were trying to live in LA 1,000 years ago, it might not have been able to expand. The city might not have been able to expand as it has now because conditions would have already been so dry. And so just kind of sum up what I've been talking about, we know that the seasonal variability in the winter storms and the El Nino events drive precipitation in Southern California. We're not sure how El Nino is going to change. There's a fantastic community of people who are working hard on this to try and figure it out. But we do have an idea of how the winter storms are going to change. And what's going to happen is they're going to migrate north, which means we're going to get fewer of those winter storms. On average, that means that our precipitation is going to drop in the next century by about 10 to 40%, depending on how much CO2 emissions we continue to put in the atmosphere and how much it continues to warm. But keep in mind that that variability is an average variability. We're still going to have that very, very wide interannual variability of very, very dry years and very, very wet years. Evidence from the paleoclimate records, so from the tree rings, indicate that we're actually living in wet conditions on average now. And in the past, it's been characterized by much drier periods. And so the question that I want to leave you with is that if we ever naturally head back into those drier periods and we combine what's happening because of humans' influence on top of it, we might be heading into uncharted territories in terms of water availability in California. So thank you.
Thank you, Branwen.
The question I have is, why are we allowing these very few people to do so much destruction in the environment, to consume so much water, which belongs to all of us? In California alone, water, that is the farmers, use about 90% of all the drinking water. And that water, by the way, has been publicly subsidized. The question, therefore, is why are we allowing this to go on?
Anyone want to volunteer? Rick, you want to start that? Maybe Heather, as a political scientist, you want to comment on the why?
Part of the answer is that we just don't have any effective federal regulation on groundwater takeouts. It's a commons, so if you have a lot of people sticking a straw into an aquifer, you have a collective action problem. Congress hasn't really taken aggressive action on it. In a lot of cases, most of water licensing or water law in terms of allocation has stayed at a state level. The federal government really has power over the interstate rivers insofar as it can the Supreme Court can appoint someone to deal with an interstate problem with a special master. That's a very long process, very acrimonious, sometimes with uncertain results. When it comes to shared aquifers, you only get litigation between the states insofar as the states can establish that there's some exchange between the groundwater and the surface waters, as you get with the Republican River between Kansas and Nebraska. Otherwise, with aquifers, you just don't have effective federal frameworks for dealing with it, and a lot of the states have really been somewhat cowardly about it. And I know that certainly in West Texas, for example, it's been a business opportunity for, say, T. Boone Pickens, who has bought very heavily into rights owned by the water conservation district. So again, your question only signals the need for an effective federal regulatory framework for groundwater takeouts and also for groundwater mapping. There are a lot of aquifers actually that aren't very well understood, as Rick indicated. So that's my best take on it. Wonderful question, thank you.
I wonder if I could just follow up on that question. I really appreciate the global perspective of this first session. It's very helpful. But I was also alarmed by the draining of our aquifers, and I'm just wondering if I could bring it home for a second and ask about the Six Basins Water Master and how effective that is in taking care of our own aquifers. Are you familiar with the details of the local structure?
Yes, from 30,000 feet. We have a fault-confined upper fan aquifer system here, which enjoys plenty of recharge. So in terms of the local population and its use of water, there's a sufficient supply for very many of us here. I think that the complicating factor is groundwater pollution and the amount of energy and money we want to put into purification. And this is an unusual situation. I want to emphasize a statistic that I gathered when I was in graduate school from a water company, WONC from Northern California, was that if we were to remove the 3 main aqueducts that are supplying water to Southern California, what would our domestic storage allow us to support in terms of a reasonable population? And of the 16 million or so people in the greater LA metro area, that's close to 6% of the American population. The number comes out roughly around 800,000, according to this estimate. And we would be in a fairly water-rich area relative to people who live, say, out in Fontana or in the central LA basin. So that's the best I can do. Are you familiar with the further?
I will say that one real, I think, good sign is that virtually every aquifer in Southern California is adjudicated. So you have courts that are establishing allocations for established appropriators who have rights to draw from that, but only insofar as their yield is deemed to be by a water master sustainable. And I will say that, you know, of the water district managers I've interviewed, they take very seriously those numbers, and they even though it is much cheaper for them to get water out of the ground than it is for them to buy it from the State Water Project or from the Metropolitan, there is a real respect for those aquifers and how critical they are for the future. And I think water district managers, in a sense, because they're part of a kind of technocratic class, they're pretty much insulated from day-to-day political pressures to take out more than they really should. So I have been impressed by the professionalism of the water masters as well as the water district folks who rely on those. So I think that's one really good sign for us.
Meryl, do you have someone on your side there? Yes.
I've lived in China where when there's a drought in an area, we read, at least in the papers, and we see from the skies, a rain produced by seeding the clouds, I think they call it. Are there human ways of controlling weather, or is this all water witching?
Yeah, wait a second.
No, we got it.
I think that's something that there's a lot of people trying to figure out. So I don't know of an answer to that question, but I do know that it is a topic of much debate. I think that there's a lot of ways that can backfire, and so I think that is a lot of work still to be done before it is an avenue we could try. Rick, to you.
In the 1950s, there was tremendous effort put into this, for instance, with seeding, as Branwen suggests. No great insights or theoretical model developed to indicate success in that regard. We do know that downwind from major cities like Chicago or Cleveland, because of sulfates, soot put into the atmosphere from coal-burning plants, yes, that will cause condensation and rainfall. But I don't know if you want to get 20% more rain in the form of a strong acid. So there are big issues there.
Okay. Gar, go ahead.
My name is Robert Newman. I'm a candidate for governor in this state, just so you know what my place is. And I'm in agriculture and have been for many years. And I know about water throughout the state of California and have studied the Delta with Schwarzenegger's Blue Ribbon Committee assigned to that task. And I've been all over California in water issues. I do hear the good professors and what they have to say. And I did hear that first question. And as a farmer, I have a strong reaction to it because I think most of you ate something today. The Central Valley Project was constructed, WPA, in the mid-30s to supply water to agriculture. We have to eat every day. Do keep that in mind, you good city dwellers. We have to eat every day. Thank you.
If the water and the precipitation is going north, and all the thirsty people are here in the southwest of the United States, and it seems like a mass migration of all the people in Southern California is not a practical solution. We don't want to go to the northwest. Can't we bring the water to the south with canals or pipelines? It seems that we have a problem maybe the planet Mars had. They were trying to build canals and it didn't work, and now there's no people there. I would hate for that to happen. So can we do some WPA projects where we build some canals and start now, don't wait for a crisis, where we all die of thirst? Do it now.
I'll take a stab at this, and I want. I really would like my scientific colleagues also to discuss the feasibility of this. First of all, I would say that California has been at the forefront of doing precisely that, of moving water from where it's abundant to where people are abundant, and we were doing this at a state level at scales that no one even contemplated would be possible for a state to do, with the State Water Project literally lifting the Feather River out of its banks and pumping it to the Delta, and then pumping it over the Tehachapi Mountains to us. I will say that it seems like a great solution, but it's extremely energy intensive. So about 20% of the energy that we're using in this state is used to pump water, to move it, and also to treat it. And also, by the time the water gets into the Delta and it's pumped out of there, and I know Brenda's going to talk a lot about this, so I don't want to discuss something that she knows so much better than I. We're talking about a lot of pollutants in that water, organics that also need to be extracted, so even quality is an issue. And then there's also the issue of what it means to alter an entire river basin. You get huge losses to evaporation. You also, when you're pumping it over a state that is riven by faults, you also are talking about the possibility for, I think the nice word is interruptions in supply. If you have a big magnitude earthquake and levees that fail, but in fact you also run big dangers of loss of life, huge damage to property and to farmland. And in so many of those rivers in the north, you have a fair number of users and claims to that water. So moving that water, even if it were technically possible, is also a big political question. The State Water Project was voted on in 1960. And it passed by, I think, 0.5%. I mean, the state, even at that point where we were so in love with the idea of growth, was still really deeply divided at that point. So, so I think there are some significant obstacles to moving water from where it's abundant to where people are living. But I want to turn to my scientific colleagues.
I have nothing more to add to that except to say that every major proposal has its trade-offs, and that quickly makes it political, not only in terms of local water users, but ecology as well, salmon runs and you name it. So it's an important question, but not an easy one to answer, that's for darn sure.
I had a question about the prediction that precipitation storms are going to be moving northward in the coming decades. The studies at UCLA on modeling suggested that the precipitation is not likely to change here in this area much in the coming decades. I wonder if you can comment on those two predictions.
Yeah, I would say that that's...
Could you take the microphone closer?
It's a reflection of how it's a science still in progress, and so it depends on what models you're looking at. None of the models are complete. They tend to focus on specific questions. And so the model that I referred to, this is studies that was done by the Southwest region in general. So it could be if you're looking at specifically LA, it's slightly different. But again, what we find is there are different studies being done and you wait till they kind of converge on an answer before you really go with that. But from what I know of, it does seem that there is leading towards a consensus that and I mean, there's evidence that it's been occurring that there will be a northward migration of the storm track. It might be that our specific location in LA is a bit immune to that, but that's, I guess we'll have to wait and see what happens over coming decades.
Okay, I think with that we'll stop. We have a 10-minute break. Our keynote speaker, Peter Glick, is here from the Pacific Institute up near Berkeley, and we will start promptly at 10:30, so you have 10 minutes. Thank you very much.